we will see that the concept of entropy will play an integral part in our study of thermodynamics. Entropy is essentially a measure of the disorder or randomness of a system. We can also take a look at entropy of the surroundings, and we'll do that later on in this video. Suffice it to say, entropy has a lot of factors that contribute to it, but really it's a measure of how disordered your system is. If we take a look at that example of my coffee losing its heat to the surroundings, we can see that at the beginning of the process, the heat is contained within my coffee. And over time, that heat disperses throughout the air, the surroundings. And so over time, that energy has dispersed. It has gone from a more orderly, contained state to a more dispersed and random state. And so it's kind of a measure of randomness or disorder of a system. And so the tendency of that energy to disperse and become random is entropy. And we'll look at defining entropy in several examples. So this is an example of thermal entropy. So where heat being in one spot, or my coffee, is being dispersed throughout the entire surroundings. So it's becoming from one space to all over. It's occupying more areas. And so there's more randomness associated with that energy. It could be located on this air particle or that one, or, versus constrained to my coffee. We can evaluate delta S, the change in entropy for a process, as the final state of entropy minus the initial state. Of course, this is not terribly easy to do. Measuring entropy is not really something we can do directly. And so we can define it in terms of things we can measure directly. Because we're going to see that the change in entropy associated for a reversible process, even though in real life things are not reversible, it's related to the change in heat for a reversible process over the temperature in Kelvin. And this is going to be at constant temperature as well. But thankfully for us, we're going to get rid of this reversible business, because we're going to note that entropy is a state function. And if you remember back to thermochemistry, state functions are ones that do not depend on the path. So however the heat is being transferred does not matter for entropy. Although for a reversible process, remember those infinitesimal changes that don't really exist in real life? There's only one path available. You can either leave the system or enter the system. There's nowhere else you can go with a reversible process. So thankfully, because S is a state function, we can just apply this at any Q. So we'll avoid all this pesky business and just make it simple. Delta S will be equal to our heat over the temperature in Kelvin. So wonderful, we can do that. Note the units, therefore, for S would be joules over kelvins, and that is your standard temperature. We can evaluate Q, as we know, in a couple of ways. We saw MC delta T for a heating of a liquid or solid or gas. However, we can't use this here because we can only calculate delta S at constant temperature. And since there's clearly a delta T, a changing temperature, can't use that one. But we can use Q for phase changes. I'll just put M for now, where M was mass or moles, depending on the units of your delta H. For us right now, let's use moles. So we're going to go ahead and write moles here. There's no temperature change with a phase change, right? So delta H fusion or vaporization, there's no temperature change. So we can use this relationship. And so we can calculate for, say, water, what the entropy associated with melting and freezing would be. So let's do this. It turns out that delta H for fusion of water is 6.01 kilojoules per mole, if I remember correctly. Yes, it is. So we have that there. At water's freezing point, which is 0 degrees Celsius, the temperature would be 273 Kelvin. We can figure this out. So for freezing water, let's just do 1 mole to make it very easy for us. If we wanted to freeze the water, we have to think, is that endothermic or exothermic? Think about it. Freezing water means we need to take its energy away, which means it's going to be an exothermic process. So the delta H will be negative. Let's take a look at the delta S associated with that. We're going to have negative 6.01 kilojoules per mole times 1 mole. Since that's our Q, right? Delta H times moles is our Q. The temperature is 273.15 Kelvin. And if we calculate this, we will get negative 22.0 joules per Kelvin. For melting water, at 0 degrees Celsius, 1 mole again, we would just have the positive of that, right? Not delta H, delta S will be positive 22.0 joules per Kelvin. Just be aware, by the way, when you're doing the math for this, you have kilojoules up top. So convert that to joules in your calculation. Right, so we end up with the opposite, which is normal, right? We'd expect this. Because as a state function, for freezing, which is the exothermic process, we're going to get a negative delta S, and doing the exact same thing for the endothermic variety of that, we will get the positive value of delta S. So we have no change here. But if we take that ice and melt it, say, at body temperature, 310 Kelvin, let's melt that 1 mole of ice at body temperature, or 310 Kelvin. You can figure it out. Delta S would be the Q, which is 6.01 kilojoules per mole, times our 1 mole, over the temperature 310. In this case, it's going to be 19 point, I have this down here, 4 joules per Kelvin. So we can melt that ice cube, right? And melting, as we know, is an endothermic process. So we're going to have a positive value of delta H with our temperature there. So, of course, that's about the system, right? This was for the ice cube itself. As we know, for the surroundings, the delta S would be the opposite, right? It's the same thing for our exothermic versus endothermic processes. Anything that happens to the system, the opposite happens to the surroundings, right? That's our first law of thermodynamics, that energy is not created or destroyed, right? It's transferred only. So in order for delta S to increase by 22 joules per Kelvin, the corresponding surroundings would lose that. So in this case, our surroundings would be the opposite, joules per Kelvin, right? Because the energy is being given off. It's exothermic. So the surroundings are accepting that. They are becoming, having a lower value of delta S. And now here's the interesting part. If we were to go ahead and freeze or melt that ice cube at 0 degrees Celsius versus at a different temperature, we're going to see that if we put these together, we'll end up with something interesting. We're going to see that delta S system plus the delta S for the surroundings, let's see if I can spell surroundings here, is going to be, no, one sec, drop this time. So if we look at the change in the system and the surroundings, we have to also consider some reality here. So for the melting ice cube at 37 degrees Celsius, we can't go backwards there, right? We can't freeze the water at 37 degrees Celsius. It's not going to happen, right? So we're going to use our delta S system for putting the energy into that system for our 0 degrees, because that's when the ice froze. We didn't get it to freeze at 37 degrees, but we got it to melt at 37 degrees. And we saw that that's a spontaneous process, right? If you have an ice cube, on your hand, although your hand is a little bit less than 37 degrees Celsius, it'll melt spontaneously. And so we're going to see that if we add those together, we have the 22 joules per Kelvin plus negative 19.4 joules per Kelvin. We're going to get positive 2.6 joules per Kelvin. And we're going to note that for a spontaneous process, the delta S of the system plus the surroundings must be greater than 0. That is going to be for an irreversible spontaneous process. This is true for any irreversible spontaneous process. For a reversible process, by the way, it will be equal to 0. And this would be at 0 degrees, right? At 0 degrees, we have no temperature change. The ice and water are just constantly reforming each other. There's no change happening. And so with no energy being added to the system, if we just happen to have ice water at 0 degrees Celsius and we're keeping it in an exactly 0 degrees Celsius chamber or something that is perfectly insulated, that would be 0, right? They're both at the same temperature, so the system and the surroundings would both be positive and negative 22.0 respectively, and so adding those together you'll get 0. And so that's for a reversible process. So this is known as the second law of thermodynamics. For any irreversible spontaneous process, the delta S of the universe, which is the sum of those two, will always increase. So I'll write that out since we like our laws. Delta S universe, which is delta S system plus delta S surroundings, must always be 0, greater than 0 for any irreversible, that means I spelled it wrong up here. Oh well. Any irreversible spontaneous process. So this just means the universe likes disorder. It likes randomness. It does not like being constrained. And we know this to be true. Take a beautifully cleaned kitchen. Now make your favorite food that you made last week. Now look at your kitchen. Look how easy it was to go from neat and orderly to completely chaotic, and how much of a pain it is again to clean that kitchen. Or think of another example. Think how long it takes to build a building. Years. Years, and a lot of energy and work put in. And how long does it take to destroy that building? To go from all those neat, orderly, I-beams and rocks and drywall to go to a pile of dust. One of them is more orderly than the other, right? A building is organized materials. A pile of rubble is disorganized. The universe always prefers that. It's a lot easier to make things more random than it is to make them orderly. And so in our next video, we'll explore that in the context of atoms and molecules.